This is EE698I, Mixed Signal IC Design, and this is lecture number 6. In the last class, we were discussing about the discrete Fourier transform, and what we saw was that the DFT is the sampled version of the discrete time Fourier transform of the signal x of n times rect of n, right? So what it means, we are taking x of n and recording it for a total of n samples, say from n equal to 0 to n minus 1, and we are taking the samples of the discrete time Fourier transform at multiples of pi by n, right? So at k to pi by n, we compute the spectrum value. Okay, so let's see what happens when we take the discrete Fourier transform for sinusoidal signals, which is our test signal for characterizing the ADC, right? So let's say we consider a signal cos omega naught n. So it's going to be a periodic signal like this, existing from minus infinity to plus infinity. So how will be the discrete time Fourier transform of the signal look like? So you'll have two impulses at omega naught n minus omega naught, right? So next, what do? We need to multiply the signal x of n with this rectangular function rect of n, so that we can truncate x of n for n samples. So how does this function look like? So this is going to have a total of n ones from n equal to 0 to n minus 1, right? And all the other samples are 0. Okay. So what is the Fourier transform of this? Well, we see that this is looking some kind of a pulse. This is looking like some kind of a pulse signal. So we can expect that the Fourier transform will resemble some kind of a sinc function, right? So, and it is not exactly sinc, so but it looks similar to a sinc function, and it will have something like this, right? And what are these frequencies where the spectrum goes to 0? Then again, we notice that to compute the Fourier transform, what do? We take the signal, multiply with sinusoids of different frequencies, and take the integral, right? So here we have only n ones. So any sinusoid which when integrated for n samples gives zeros are these frequencies, right? And what are those sinusoids? Well, any sinusoids that completes integer number of cycles within these n samples will give 0 when integrated, right? So the minimum frequency will be 2 pi by n. The second frequency will be 4 pi by n, and so on. Okay. So in time domain, we are multiplying these two signals. So in frequency domain, the spectrum will convolve. So what happens here? We have cos omega naught n for 0 to n minus 1 samples, right? So here we'll have something like this. Okay. Again, please note that these are all discrete samples. Okay, so only for simplicity, I am representing them as some continuous time signal. Okay. So how will the spectrum look like? It will be convolution of these two spectra. So what we'll have this spectrum shifted around to these two frequencies, right? So for simplicity, I'll just show around omega naught. So around omega naught, we have this, something like this, right? And what is this frequency? This will be omega naught plus 2 pi by. Okay. And finally, to find DFT, what do we need to do? We need to sample this spectrum at k times 2 pi by n. So let's see what happens. So let me move to the next page. So I'll draw the spectrum again. So this frequency is omega naught, and this is omega naught plus 2 pi by n, right? And this frequency is omega naught plus 4 pi by n, right? Now let us say I choose the input frequency to be omega naught equal to m times 2 pi by n, right? And m and n are integers and are co-prime. Okay, so what happens? Well, this is now m times 2 pi by n. So this frequency, what is that? That will be m plus 1 times 2 pi by n, and this will be m plus 2 times 2 pi by, right? So to find the DFT, we are going to sample the spectrum at k 2 pi by n. Okay, so what will happen? At this point, we'll be sampling this m 2 pi by n, so we'll have this sample, and the next sample will be here, that will 0. The next sample will again be 0, and all the other samples will similarly be equal to 0, right? So finally, what we'll have will end up, if this is k, again this is omega axis, this is k axis. So we'll have one impulse at k equal to m, right? That is this, and all the other points will be 0, right? Again, at the negative side, we'll have one at minus m, one impulse at minus m. So if I'm showing from k, if I'm showing k from 0 to total of n minus 1, we'll have the impulse at some n minus m, right? So we'll have two impulses as we expect. Okay, and this scenario is often referred to as a signal falling on a bin, right? That is, the input frequency exactly corresponds to one of these bin frequencies, right? That in this case it is m. Okay, so let's look at an example. So here what I've taken is a signal x of n equal to cos 201 by 1024 times n. Okay, and I'm taking a 1024 point DFT. So what do I expect? I expect two impulses, right? And that's what we get. We get one impulse at the bin frequency 201, and one more at n minus 201, that is 1024 minus 20. Okay. So in this case, what we chose the input frequency as 201 by 1024 times 2 pi, right? So which means I've chosen the ratio of the input and the sampling frequency as what? 201 by 1024, right? So which means I have chosen Fin to be 201 by 1024 times Fs. Okay. So in practice, obviously, these two frequencies, that is the input frequency and the sampling frequency, will be generated by two separate signal generators, right? Okay. And as you will be studying in some other courses, these two, I mean, if you don't do anything, the oscillators, that is the frequency of oscillation of these oscillators, will keep drifting over time. Okay. So what do we have to do? We need to make sure that these two sources are synced somehow, right? So in practice, what do? We can sync these two sources. Okay, so that what happens is that we can maintain the ratio Fin by Fs to be constant. Okay, so it might so happen that in practice, one source, the frequency of one source might change to some, say, alpha times Fin, right? But if we sync both of them, what will happen? Even the other source frequency will shift by the same amount, so that the fraction Fin by Fs does not change. Okay. And in some cases, you might not be able to do this. And even if you do it, there might be some error, right? So let's say what happens, let's say our input frequency omega naught turns out to be 201.01 by 1024 times 2 pi, right? So that means Fin by Fs is what? 201.01 by 1024. So what will happen? Well, so let me push it up. So till this point, that is, till this point, we have the same, right? We are multiplying cos omega naught n, where omega naught has slightly changed, and multiplying with this rectangular function. So I'll get this spectrum, right? So let me draw that once. So this is my omega naught. Okay. And this will be omega naught plus 2 pi by, right? And let's say in my case, n is 1024, it's 1024, right? But what is omega naught? It is this value. So this is going to be 2 pi times 201.01 by 1024, right? So which means this value is what? It's going to be incremented by 1. So it will be 202.01 by 1024 times Fs. Okay. And as usual, what we are going to do, we are going to sample the spectrum at k times 2 pi by n. That is k times 2 pi by 1024. So what will happen? Well, we will try to sample it at k times, 201 times 2 pi by 1024, right? And that will be, this frequency is what? 201.01. So 201 will be somewhere here. So we will take one sample here, right? And the next sample will be taken at 202, right? So this null is 202.01. So 202 will be somewhere here. So similarly, I will take these samples. Okay. So instead of sampling all these null values, that's what was happening in the earlier case when we chose the input frequency to be 201 by 1024. So in this case, what's happening? We are sampling slightly away from these frequency nulls. Okay. And you will get some kind of a spectrum like this, right? And this phenomenon is often referred to as FFT leakage. So let's just confirm this from simulations. So here I am showing two plots. So this is when my input frequency is 201 by 1024 times 2 pi, right? Again, this is a 1024 point DFT. Okay, and the second curve is when I change the input frequency slightly to 201.01 by 1024 times 2 pi. Okay, and we clearly see that the spectrum shows some kind of a skirt like this. Right? So, well, let's say if you are giving such an input to your ADC and measuring the spectrum at the output, what you will think? You will think that this flat portion is due to the quantization noise, right? So even though your ADC might be doing an excellent job, let's say it's an infinite resolution ADC, and in the actual noise spectrum is this, it's so low, just because you didn't do your FFT or you didn't choose your input frequency properly, what's happening? You're having a very higher, like all the other bins that were supposed to be 0 are now completely filled with a high value, and you will mistake it for quantization noise. Okay, so how to solve this problem? Well, from frequency domain, it doesn't look like we can find a solution to this problem, right? So what we'll do is we'll try to understand this problem from time domain with the hope of finding some solution to this. Okay, so in the first case, what we did, we chose a frequency that is 201 by 1024 times 2 pi, right? And we took a total of 1024 samples and computed a 1024 point DFT, right? So let's say this is my window of 1024 samples. Say this is n equal to 0. This is n equal to 1023. Okay. So in this window, how will the sinusoid look like? So it will be some signal like this, right? And it will exactly complete a total of 201 cycles, right? Within this 1024 samples. Okay. And of course, the period of the signal is what? That is also 1024, right? So in the last class, we saw that DFT, even though the signal is truncated to a total of n samples, which in this case 1024 samples, it assumes that the signal is periodic with this period, right? So what it will assume is that we have the same signal that is repeating after and before. So we'll have the same signal going like this, right? And for this periodic signal, it computes the spectrum, right? So since in this case, the period of the signal is also 1024, we'll have a smooth sinusoid going like this, right? But let's say when I change the frequency to 201.01 by 1024 times Fs, 1024 times 2 pi. So obviously this signal does not have a period of 1024, right? And what will happen within 1024 samples? It will complete a total of 201.01 cycles, right? So it sort of finishes 201 cycles before, 201 cycles well before, and it goes well below that, right? So what will happen now if I try to have a repetition of this signal? I'll start having a sudden jump at this point and it will repeat, right? So similarly at this end, the signal will end here and there will be a sudden jump here, okay? So since we have the sudden jump, we know that the sudden jump corresponds to high frequency, right? So this sudden jump is what results in this kind of a flat high frequency noise, okay? And that's what is happening in the time domain, right? So how do we solve this? Well, we observe that in this window of 1024 samples, all the samples in between are fine, right? We're having issues because of the sudden jumps at the ends, that is at the beginning and the end. So the idea is to make sure that the samples at the end, that is both at the beginning and the end, are weighted less compared to the middle sample. So what we do, instead of taking this entire chunk of data as it is, we will weight them such that the weighting function does something like this, okay? So see, this is 1, this is 0. So it gives very little weightage to the samples at the end, right? And gives maximum weightage to the samples in between, okay? So if we do this, these discontinuities around the edges will reduce significantly, and we hope that this effect of having this FFT leakage will also reduce eventually, okay? And obviously there are many number of ways to generate this kind of a function, and one such common function is called hand window or a raised cosine window, okay? So this window looks something like this. So it looks like a sinusoid. It is a sinusoid. It's doing something like this, okay? This is a total of n samples, 0 to n minus 1, right? So obviously this looks like an inverted cosine, right? And what is the frequency? It completes one period in a total of n samples. So the frequency is 2 pi by n times n, right? And this goes from 0 to 1, right? So we need to shift it by 1 and multiply it by half, okay? So what we have to do in this case, if you use this window, we need to take the signal, that is x of n times rect of n, and then multiply it by this function, 1 minus cos 2 pi by n times n. Okay. So let's see what happens when we apply this window. Okay, we'll first consider a case when the signal is lying on a beam. Okay, that is when we choose signal of the form cos 2 pi times m by n times n, right? Where again m can be 201 as we saw in the example earlier, right? So what we are doing here, we are multiplying this with a rectangular window, right? And this act of multiplying with rectangular window, it can be simply modeled as we take the samples from 0 to n minus 1, right? So the next thing is we are multiplying with this hand window, that is 0.5 times 1 minus cos 2 pi by n times n. Okay, so what happens when we simplify? So we have 0.5 times cos 2 pi m by n times n, we get the input, minus 0.5 times we get product of these two cosines, right? So if we expand the product of the cosines, so what we get half times cos of the sum frequency, that is sum of these two frequencies, which is what, 2 pi by n times m plus 1 times n, plus we get the difference frequency also, 2 pi by n times m minus 1 times n. Okay, so what will happen if you take this spectrum? Well, now instead of having one sinusoid, we have 3 sinusoids, right? So the spectrum will have impulses, the discrete time impulses at mth bin. That corresponds to the input sinusoid. We also have a sinusoid at a frequency m plus 1 times 2 pi by n. So even at m plus 1, we'll have an impulse. Similarly, at m minus 1, that is this, we'll have an impulse, right? And we can clearly see that the strength of these two sinusoids is 2 times smaller than the main sinusoid, right? So this will be 6 dB lower if you take in the log scale. Okay. So what this means? Well, when we took just a rectangular window, and in the case when the input was falling on a bin, so we just had one impulse, right, at m. Okay. Now compared to, when we do hand window, what happens? The signal spills over to 3 bins. Right? And obviously in hand window, with the rectangular window, if this had a strength of say 1, I'm just normalizing it to 1. So here what it will be, this will be half, right? And this will be what? 0.25, right? So one thing to observe is that when we are multiplying the signal with this hand window, so the maximum value is 1. So this is 1, right? And what we are doing, we are giving lesser weightage to the samples at the edges, right? So we kind of expect that the power of the signal after multiplying by hand window should be lower, right? So, and that's what happens. So let's see how much the power is actually getting reduced by. So with the rectangular window, so we had a signal of the form cos 2 pi times m by n times n. What is the power? It is half, right? And with a hand window, when we have a similar signal, what happens? We multiply it with this function, and we end up with 3 sinusoids like this, right? So let me just mention the frequency of the sinusoids. The first frequency is 2 pi times m by n, and the amplitude is 0.5, right? So I have a 0.5, sinusoid with an amplitude 0.5 and a frequency of what? 2 pi times m by n, right? So what is the power of this? It's going to be half into 0.5 squared. That is simply 1/2 of 1/4, right? So we have the other two sinusoids at m plus 1 and m minus 1, and the amplitude is 1/4, right? So we have 2 more frequencies, 2 pi by n times m plus 1 and 2 pi by n times m minus 1. Okay, and the amplitude of these sinusoids are what? 0.25 and 0.25, right? So each of them will have a power of half into 1/4 squared, which is half 1/16. So similarly, this will also have this, right? So what is the total power in the signal? That is sum of these. So that is half of 3/8, right? So with the hand window, the power of the signal is reduced by a factor of 3/8. Okay. So with the rectangular window, when the signal was falling on a bin, you would have just got one impulse at bin m, right? I'm just showing only one positive half of the frequency. Okay. I'm not showing the other impulse at n minus m. Fine. I'll just not show it. Right. And to find the power, what we have to do? Well, in the last lecture, we saw that we can compute the power using this formula, right? That is mod Fourier transform squared times 1 by n squared, and we vary k from 0 to n minus 1. So what we do, we vary k from 0 to n minus 1, right? And in this case, for a sinusoidal signal, the power is in only this bin, and of course the other bin at n minus m, which I'm not considering for now. So what we'll simply do is we'll take the magnitude squared of the mth bin and multiply by n square, right? And this will give me the power of the sinusoid. With the hand window, what happens? Well, we'll have 3 sinusoids, right? So if I look at the discrete Fourier transform, I'll have 3 impulses like this, right? So to find the power, what I'll have to do, I'll have to sum up the power in all these 3 bins, right? So what will that be? I'll have mod x of k squared, and I have to vary k from m to m minus 1 to m plus 1, right? And okay, let me put it here. And I'll have to divide by n squared, and then I'll have to scale the total power by 8 by 3, right? This will only this will give the true power of the signal. Okay. So enough of this calculation. So let's see in simulation what we get. So here I am showing, here I'm considering the case where again signal is lying on a bin. So again, the signal is cos 2 pi times 201 by 1024 times n, right? So the red curve you see here, or you can see here also, that is corresponding to the rectangular window case where I'm not doing any additional windowing. I'm just truncating the signal to total of 1024 samples, right? And the magenta, the pink curve, that is after I apply the hand window. Okay, so this portion here I have zoomed in and showed here. Okay, so with the rectangular window, I see only one impulse here, right? And with the hand window, the signal is spilled to these 3 bins, right? And you can clearly see that this is in dB, right? This is in log scale, the y-axis. So this is 6 dB lower, right? Compared to the rectangular window case, the strength of the impulse, the value of the impulse at the 201th pin is 6 dB lower in the hand window case, and the other 2 bins on either sides, they are further 6 dB lower. Okay, and that's what we expect from our calculation as well, right? So next, let's consider the case when the signal is not lying on a bin. Okay, because that was our actual point. That was the reason why we considered choosing a hand window, right? So let's see what happens when signal is not lying on a bin. And again, we'll take the case where omega is 201.01 by 1024 times 2 pi. Okay, so let's see what we get in simulation. Okay, so the red curve here again shows only for the rectangular window case. That is, I'm just truncating the signal from 0 to n minus 1. Again, the frequency is 2 pi by 1024 times 201.0. Okay, and this magenta curve is after I apply the hand window, right? And I can clearly see that these curves which were appearing with the rectangular window have reduced a lot, right, with the hand window. And that's what we intuitively expected with the hand window. Okay. So in practice, there are, as I mentioned, there are infinite number of ways in which you can weight the samples, right? The goal is to make sure that we give lower weightage to the samples at the edges and give maximum weightage to the ones in the middle. Okay, so we can have any number of windows. And besides hand window, one other window that we commonly use in ADC measurements is what is called the Blackman-Harris window. Okay, so this Blackman-Harris window can reduce the effect of these skirts even further. Okay, so with a rectangular window, let's say we got some skirt like this. Okay, when we used hand window, it reduced like this, right? And if you use a Blackman-Harris window, it can further reduce like this. Okay, but the trade-off is that when we used a hand window, the signal spilled over to 3 bins, right? A total of 3 bins. And with a Blackman-Harris window, it will actually spill over to a total of 7 bins. Okay, so that is the trade-off. So if you want to make sure that the skirts become shorter, I mean, the effect of this cut is reduced further, what will happen? The number of bins to which the signal is getting spilled will increase. Okay, so that's the trade-off. So this figure here shows the effect of Blackman-Harris window. So again, the frequency is the same. It is 201.01 by 1024 times 2 pi. So this is again with the rectangular window. So this is with the hand window. And the black one with the Blackman-Harris window. Okay, and we clearly see that the skirt here is further reduced. Okay. So now we have discussed what happens when we take the discrete Fourier transform for the sinusoidal test signal, right? So let's see what happens when we what happens to the spectrum of the quantization noise when we use the discrete Fourier transform. So what we do for measuring, I mean, for characterizing the ADC, we feed a sinusoidal signal of the form cos 2 pi times m by n, right? Into it, sorry. And we collect a total of n samples and take the discrete Fourier transform, right? So because we are feeding such a periodic signal, even the quantization noise will also be periodic with the same period, right? So what will happen is within this window of total of say n samples, this is say 0 to n minus 1, you might have some quantization noise, something like this. I'm just drawing some rough sketch, right? And with the what the DFT assumes is that we have a periodic repetition of this same set of waveform on either sides, right? So because we are making sure that the signal is also periodic, even the quantization noise will be periodic, and there will be no jumps when you extend this on either sides, right? So that there will be no problem of this FFT leakage and stuff if we ensure that the signal is falling on a bin. Okay. But along with the quantization noise, we also have random circuit noise, which obviously cannot be made periodic, right? Which is not periodic. That is totally unrelated to the signal. So what will happen is the random circuit noise, I don't know, might look something like this. Okay, so if you capture only for a total of n samples, like this, say it ends like this. Okay, so we'll have a repetition of this. So we'll have the same chunk repeating on either sides. So on this side, we'll have a sudden jump here and it will do something. Again, here you'll have something and okay. So again, we'll have the sudden jumps here. Okay. But what happens in practice is that since we are dealing with a white noise, that is the power spectral density of the circuit noise itself is white and flat like this, these jumps will also result in some kind of a white flat noise, right? That's what we saw with the FFT leakage. So the effect of this might be smaller, okay? And what will happen? This will not finally affect the spectrum estimation. Okay, so as long as we are dealing with white noise, these sudden jumps might not make a big difference in many cases. Okay. So finally, to our ADC, if we feed a sinusoid of the form cos 2 pi times m by n times n, at the output we'll have the same sinusoid plus the quantization noise, right? Plus obviously some circuit noise will be there, which let's not consider for now. Okay, so if we compute the power spectral density, again, let's take the one-sided power spectral density. And how do we compute? 1 by n times mod x of k squared, and we'll take multiple averages of this using the Welch estimate, right? So how it will look if we made sure that the sinusoid is lying on a bin, the output spectrum will have one impulse, discrete time impulse corresponding to the mth bin. Again, this is k. Okay, and we'll have the quantization noise filling up the rest of the bits, right? And to find the signal power, what we have to do, we need to find the strength of this impulse, right? And scale it by a factor of n. That is, if I call this as, say the output is v, I'll call this SV of k. So this is SV of m, that is the mth, right? And this is essentially what? 1 by n squared times mod x of m squared. Right? Again, you can take multiple averages of this. Okay, so this is going to give me the signal power. Right? This is my signal power. And what about the noise power? Well, we take the sum of all the other bins. Okay. And that's going to give me the noise power. Right? So what I'll do? I'll do the same thing. I'll take summation of all the other bins except the signal bin. Or I'll just say k not equal to m, right? 1 by n times sp of k, right? So this is again equal to 1 by n squared summation k not equal to m or x of k squared, and this is sort of averaged, right? And the ratio of these two will give me the signal to noise ratio. Okay, and in practice, again, since we are considering only the ratio of the two powers, we can sort of ignore the scaling factors. Okay, so in practice, to compute the ratio, you can just take the magnitude squared of the DFT, right? And say the signal power is proportional to the magnitude of this impulse, right? And some of the other bins will give me the noise power, right? Proportional, that will be proportional to the noise power. And this will be proportional to the signal power. And you can just take the ratio of these, right? So if you use the hand window, what happens? And if the signal is also lying on a bin, what will happen? So we'll have an impulse at m. We'll also have two other impulses on either sides, and rest all will be due to the quantization noise. Right? So here the signal power will be sum of these three bins, right? So sum of these three bins will give me the signal power that will be proportional to the signal power, and the sum of all the other bins will be proportional to the noise power, right? And we'll take the ratio of the two to find the signal to noise ratio. Okay. So to summarize the discussion about the windows, so if we can make sure that the signal falls on a bin, that is the ratio of the input to the sampling frequency is of the form m by n, where m and n are co-prime. Okay, like we had this case of 201 by 1024. We don't need to do any windowing, right? And again, if you use and if you're dealing with white noise, so we don't have to use windowing. Okay, so if these two cases are satisfied, in practice, windowing might not be needed. Okay, and this can be satisfied in simulations, right? Especially the first case, right? In the first case, we need to make sure the input frequency is of the form m by n times fs, right? Or in the example we chose, it has to be something like this. So this can be exactly satisfied with simulations, right? Again, in simulation, you need to be careful. We need to, you should not expand this fraction. That is, you should not simplify this fraction and write something like, this might be 0.199 or something, right? So don't, simplify this fraction and give the value as this, okay? Should retain the frequency as exactly this, right? And if you do this in simulation, we can ensure that the signal is exactly falling on a bit, right? But when you try to measure in practice, we might not be able to satisfy this, and we'll have to use some kind of a window. It can be either Han or Blackman-Harris. Okay. So one last thing regarding windows. So till this point, we are dealing with cases where the noise power spectral density was flat, right? And that's why even without windowing, it seemed fine, right? So we saw with white noise, even though there were jumps, right? When you have the periodic repetition, right? We saw that the flat noise that might be introduced by these jumps, they might be very small in practice compared to the actual power spectral density of the white noise, and so they might not be of any consequence. Okay, but as we'll see in later classes, we'll be dealing with special kind of ADCs called noise shaping ADCs. Okay, so where the noise spectrum will not be flat. Okay, so how it will look is as follows. So if we give a sinusoid, we'll have one sinusoid here. Okay, and that quantization noise, what will happen is that it will be high pass shaped and it will have a spectrum like this. Okay, so because of this, what will happen? Again, this quantization noise, even though your signal is periodic, in noise shaping ADCs, the quantization noise might not be periodic, right? So what will happen? We'll have these sudden jumps like this. Okay, and this sudden jump, as we expect, will introduce some kind of a flat noise like this, right? So what will happen because of this? This entire spectrum will get distorted. At low frequencies, it will be filled by this, like flat portion, and you'll have some overall spectrum like this. Okay, and this is not exact. I mean, this is not obviously the spectrum we should have got. The actual spectrum must have done something like this, right? Because the noise is getting high pass shape. At DC, ideally it should have been 0, right? It should be very low, but because of this abrupt change, what happens? Within at low frequencies, we have this flat portion. Okay, so to confirm this, let's look at some simulation result. So this is just a pure sinusoid. Okay, so this is the spectrum of a pure sinusoid. Here I'm showing only one side, that is one-sided spectrum. Okay, so this is the case where we just have a pure sinusoid. And this red spectrum, red curve corresponds to the spectrum where we have a sinusoid falling on a bin, right? As that is same as this case. Okay. Plus we have this high pass shape noise. That is high pass filtered noise. Okay. So please note that even though the signal here is exactly falling on a bin, because of the fact that we are dealing with this kind of high pass shape noise, when we are doing this rectangular window, that is when we are simply truncating the sequence to n samples, we have this flat portion in the spectrum, right? So in this case, what we have to do, we need to smoothen this abrupt jump by using some window functions, right? And the moment I use a hand window, that is with the magenta curve, I see that we get back the spectrum that we actually would have got properly, right? So this is the expected spectrum, and that's what we get. Okay. So what happens with noise shaping ADCs? So we'll see one example as delta sigma ADC. So in this case, what we have to do, even when we are doing simulation, we need to ensure that we are taking hand window. Okay. This is because even though you make sure that your signal might exactly fall on a bin, the quantization noise is getting high pass filtered. So any abrupt jumps will result in a flat spectrum at low frequencies, right? So in short, when we are dealing with flat noise, that is a noise which has a flat spectrum, it might be okay even if you don't use any window. Okay, but whenever the noise spectrum has this kind of nulls at any frequency, right? In this case, I assume that the noise has a null at DC at low frequencies. But but there might be cases where you might be dealing with ADCs where the noise has nulls at some other frequency. Okay, so in any case where the noise spectrum has nulls, you need to make sure that you use some kind of a window. Okay, so let's stop here and continue from the next class.